All right, so let's have a look at this one. Right, this is the Redox Equilibria question for 2010, and we're basically asked to do the same thing that we just did in 2015. Right, literally the same thing. So somebody can tell me what the standard electrode potential of a half cell is. What is that? Oh, what I'm seeing in the chat, that's possible. It's possible. Because you know it's your Clanche cell, your lead acid accumulator, and your fuel cell. Those are three examples that are given in the syllabus for this topic. Your Leclanche cell is a regular primary battery. Your lead acid accumulator is a secondary battery, right? And your fuel cell is a fuel cell. It's not a battery. I mean, just to name them, I guess there's different characteristics. The Electron cell is a primary battery. That means that it cannot be charged. After it's discharged, it's done. Your lead acid accumulator is what we call a secondary battery. Like your phone battery is a secondary battery because it can be recharged, right? And then your fuel cell then definitely, right, cannot be recharged generally. Or, well, it's not seen as charged or recharged, but we use fuel in order to actually generate electricity in our fuel cells. Leclanche cell, lead acid
Sir,
accumulator,
there's a
those stuff. Go ahead.
sir for this paper. There's another vanadium question for
Mm,
module 6. Yeah.
yeah. Oh, okay. All right. Let's go. Standard electrode potential of a half cell. What is that? So it's electrode potential. It's a potential difference measured across, well, measured at a half cell or from a half cell when it is attached to a standard hydrogen electrode under standard conditions. And the standard cell potential of an electrochemical cell is the combined potential difference measured when two half cells are combined, right? And here now we are asked to touch the diagram to label the diagram, right? So basically what we're gonna do here on figure one, label this, all right? Okay, so that's what we're going to have here now. Where is the cathode and the anode, right? If this is copper, yeah, if this is copper, let me just put this as copper. If this is copper, then this is copper 2 plus. That's 2 plus. And then if this would be aluminum. Why am I put it like that? Because generally we like to be in the ABC format, anode before cathode, right? So Al, right, and 3 plus. So in that case now, this is our cathode, right? This is our anode, right? And in that case now, this is our salt bridge. We know that this is our salt bridge. That's our salt bridge, right? Direction of electron flow would be this way. Our electrons will be moving in this direction. So when we see our electrons, they will be moving that way. Solution, ions for solution A. Oh, well, those are the ions for solution A. So let's call this A and let's call this B. Those are our ions there. Moving on to the next page. State what would be observed at the cathode for the electrochemical cell if it's running for a few hours. What will be happening at our cathode? We're going to see a color change, yes? It's going to be decolorized. We're going to see blue to colorless. What's happening? We're going to have blue to, let me not write that, to colorless, right? And that's because we're gonna have carbon, well, not carbon, copper being redeposited back onto the electrode. State the experimental conditions for the preparation of this cell. For the temperature, right, it must be 298 Kelvin, right?
or 25 degrees.
Whereas, as a scientist, I do not believe in Celsius. All right, lovely. I do not believe in such units. It's like you're telling me that a building is 500 giraffes high. Like, it sounds like an American. All right. All right. So, conditions here, we're going to have 1 molar for both. 1 mole per dinky for both. All right, lovely. You can put the 25 centimeter, well, not centimeter, 25 degrees Celsius if you want. All right. But 298 Kelvin. Yes, lovely. So from the data booklet now, calculate the standard electrode potential. And now this is what a question I can't do unless I have a data booklet. Usually we send around the copy of the actual data booklet you'll get in the exam through WhatsApp groups. But I don't see it being sent this year and I'm not sure why. Why are you guys not more resourceful as we were? Where are the data booklets? Anybody have any data booklets? Nobody has any? Guys need to be resourceful.
Do you have any?
Oh, I don't. I don't have any. I don't have it anymore. No, it's not that we carry our own. It's that somebody, I don't know who did it, but somebody scanned the entire data booklet that you will get in the exam, and then we had the thing circulating. But I don't. Oh, there it is. Lovely. All right. Look at that. Is Lapa understand that? Beautiful. So you can now look at the information that you do not need to memorize and know that you're cool without them. Alright. So we even have constants and ionic and atomic number, well, radii for our groups. I lie. And we have ionization energies as well. Who can't fail this exam? Look at information.
Sir, not too much now. Not too much.
Look at information. Alright, so from the data booklet that I'm looking at now, we're supposed to calculate the standard cell potential, right? So we have, what we're having is aluminium and copper, right? So we know that E cell, E naught of a cell, is going to be equal to cathode, cath minus anode, right? Therefore, our cathode, right, is a copper going to 2 plus. So therefore, at our cathode, we have a reduction happening, right? And our copper is actually plus 0.34 volts. And what we're doing is now minusing aluminium. Aluminium is actually beneath copper. Oh, wait, hold on. No, aluminium should be above. Where is the aluminium? Yeah, aluminium is above copper, and we need to change around that value. So what we're going to end up doing is changing the negative 1.66 to positive 1.66 volts, and then we should get our answer. So here now we see 0.34 minus 1.66. Our answer is negative 1.32 volts. School is over. Alright. Nothing more to this question, and we move on with our lives.